Hello everyone and welcome to our fifth webinar in the Taming the Dragon series. My name is Daniela and I'm part of the marketing team here at Zetascale, and I have the pleasure of introducing Julian, who is our senior solution architect and who will host today's webinar. He'll be talking about how easy it is to integrate Zeno with databases and messaging protocols and how it makes it easier for you to build cloud to thing applications. Just before we start, a few reminders. I'll add the recordings of the past webinar session in the chat in a few minutes, and you'll receive an automated email with the recording for this session at the end of the webinar. If you have any questions, please leave them in the chat, the comment chat that's on the right side of your screen, and Julian and I will answer them at the end of the session. I can see we already have over 10, 15 people joining in online, so I won't take any more of your time. Julian, the floor is yours.
Thank you, Daniela. Hello, everyone. So today in our series about Zeno and what you can achieve with Zeno, we'll talk about integration of database. So mainly the Zeno storages, Zeno backend and storages, and how they can be used with Zeno and with other protocols that are bridged to Zeno, as we demonstrated in the past sessions. So just a quick recall on the previous episode of Zeno. You have all the links to recording here in the handouts that you'll have access to. So we have a first view on the Zeno genesis, where we are coming from and how we came to this new protocol on this new middleware, which is Eclipse Zeno. And then Luca made a quick getting started on what you can achieve with Zeno, or what are the concepts behind Zeno and how you can use them in a lot of various use cases. On the 6th of December, I made a presentation on robotic, on how we bridge ROS2 with Zeno, but not only ROS2 with DDS, Data Distribution System, which is used by ROS2, which is a pub sub-mechanism also bridged to Zeno, and also MQTT. I made a presentation. If you didn't, so I encourage you to watch the recording. I made a demonstration of integration between ZigBee, MQTT, Zeno and DDS ROS2. So to summarize, because that will be also the topic of this middleware, of this presentation, the Zeno middleware allows to bridge some protocols which are also publication and subscription, and so all messaging protocol can be forwarded to Zeno, and Zeno can also store the data, as we will see in this during this presentation. On the December 13th, my colleague Carlos made a presentation on Zeno on microcontroller with the help of Zeno Pico and also on low power network. And today, let's go with integrating database, so Zeno storages. So quick reminder of the Zeno benefits with regard to topology of deployment. Zeno can be deployed in peer-to-peer systems. So you may have all your application communicating directly with each other, either in a click where all peers are connected to each other, either in a mesh topology of peers, like here in upper right, where all the peers are not necessarily connected with each other, but you may have some peers which act as a router between two peers to mediate the messages and the queries also. We support also broker mode and routed mode via Zeno router, which can be interconnected also in a mesh network. So you might mix all of this together to make complex system with subsystems using peer-to-peer, still connected to the internet, for instance, or to the edge of cloud computing with the help of routers, of different routers for fault tolerance, for load balancing possibly. And all of this give you the possibility to create really complex systems. So with regard to the primitives that Zeno supports publication and subscription in push mode, but also subscription in pull mode, where the subscriber will pull the latest data that have been published at its own pace. So when he wants, he pulls the latest publication. And Zeno support also publication, storage, and retrieval of the previously stored publications. So in Zeno, you can introduce what we name as storage in the system. All the publication will go to the publication you want will go to the storage, and later on, any application can retrieve a past publication from this storage. And with the same mechanism, we support also get and reply in order, for instance, to implement query and reply for RPC, for instance, but also for other mechanisms where you need an interaction with between two peers. So now let's focus on storages. So what is a storage in Zeno? So when I declare in Zeno a storage on a key expression, for instance, room/**, I mean I want to store all the publications that are matching this key expression. So when I perform a publication on room/2/hum for humidity and value 42, I want this publication to be stored in the storage, and later on I want any application to be able to retrieve this publication or other publication also that matches any query I may want. So for instance, here I do a query on get on room/**/hum. So I want all the humidity measurements in all the rooms of my house or my building. So how is it implemented underneath? Well, actually, a storage is at first a subscriber, because you need the storage to subscribe to any publication made on this key expression. And in addition, it is also a queryable to answer, to reply to the queries coming from the peers. So already you see that with the simple primitives that we have in Zeno, publisher, subscriber, queryable, getter, that performs the gets, we can implement this storage concept. And how is it implemented actually in Zeno? It's implemented with via a plugin. So in Zeno, as we saw in a previous episode of our webinar, you may have different plugins that are implemented in Zeno that are a dynamic library loaded in the Zeno router. And there is actually a specific one for the storages, which is named the Storage Manager plugins, which is actually delivered, released with the Zeno router, so available at need for you when you deploy your Zeno router. And this Storage Manager plugin will be able to manage the storages depending on various technologies that you may want to use to store your data in various databases. So now, how can you configure this plugin and the storages that it can provide? First, a little lexic on the concept that we introduced in Zeno. So you have the Zeno router, which deployed the Storage Manager plugins. And the first thing that you need to configure is which backend to use. So what is a backend? A backend in Zeno is a dynamic library which is specific to a storage technology. So that's really the implementation library of all the storages for a certain technology. So for instance, you may have a backend for RocksDB, for InfluxDB, or to store data simply in a file system. So you can see here we have different libraries. So here two backends are loaded. The InfluxDB backend and the file system backend. A volume. So a volume in Zeno is a backend instance with a specific configuration for a set of storages. So for instance, you may have for InfluxDB a URL to the database, to the InfluxDB server that you want to connect to. You may have also some credentials that is configured. In the case of the file system, it will be, for instance, a root directory where all the storages will store their data, and they will not be able to store anywhere else that in this directory. And you can imagine also to have several volumes instantiated for a single backend. For instance, if you have several InfluxDB server, you might need to declare one volume per InfluxDB server. So that can be useful in this way. And then a storage. A storage is a space within the volume to store the Zeno publication. So what you do when you declare a storage, you first declare its key expression. So the key expression it will subscribe to, but also this same key expression, it will reply to queries for the querier to get back the historical publication. So for instance, a storage host on tmp/**, we can configure it specifically in InfluxDB to have all the publications stored in a database table named temp_db. Or for the file system, for instance, you will configure a subdirectory of the volume directory to store all the data specific to this storage. And you can declare as much storage you want in any of the volumes that have been declared. The backends that we currently have available in Zeno. The first one is memory. So memory backend is actually just a hash map in the memory of the Zeno router. For this one, there is no specific library to load because the code is so simple that it's already embedded in the storage manager plugin. So no need to specify a backend to load, and no need to specify a volume because there is only one volume, which is memory volume, in which you will have one hash map per storage. The file system storage backend is another example. So in this case, each publication made in Zeno that will be stored in an individual file. So you will have one file per key of publication. Meaning that, for instance, if I have a file system storage on demo/**, I then made a publication on demo/a/b. In the file system, it will create a file named a/b, so a directory A on a file B under this directory. And the value of publication will be exactly copied in the content of the file. So you may have, for instance, publish a raw JPEG file, so a buffer of JPEG in Zeno, and it will be stored exactly as a JPEG file on your storage file system. By default, the file system storage will store everything in an environment variable that you can configure at Zeno router startup, and which will by default be in the directory displayed here. So in your home directory .zeno/zbackendfs, which is the name of the backend library. RocksDB. So RocksDB is a database technology, a key value store, which stores on file. It's really efficient, and there is a Rust API for it that we leverage in the RocksDB backend. So everything will be stored on disk in an environment variable within a directory, and this directory is configured per storage. So when you declare a RocksDB storage, you declare the subdirectory that will be used for the RocksDB database. And here you have the default path for the root of all storages using the RocksDB database. We also support InfluxDB. So InfluxDB is a time series database. So usually it's deployed in a server that is reachable via HTTP. So when you declare your volume, you specify the URL, HTTP URL to connect to this InfluxDB server, and Zeno will take care to forward all the publication to this InfluxDB server, but also to forward queries to this InfluxDB server to retrieve the data that you want through Zeno. Recently, we added also a new backend based on AWS S3 API, so not only tied to the real the Amazon AWS S3 backend, but also compatible with all databases that leverage the S3 APIs. For instance, MinIO is a non-Amazon database that still accepts S3 API, so you can use the backend S3 with MinIO. So now a little more detail on how this storage can be configured. So in the configuration file, so the JSON5 file configuring the router, you have the plugin sections, and in this plugin section you have one for the storage manager. And in this storage manager section, you have a section to declare the volumes. So for instance, here we declare two volumes, one for InfluxDB and one for the file system. And you can notice that I highlighted in blue the InfluxDB name and the FS name. So because by default, Zeno will look we search for the library named according to this pattern, which is libzbackend underscore the name of the volume, so the name of the backend that you want, .so. So of course, on Mac OS and Windows, it will be different prefix and suffix for the file, but still the concept is that a backend is supposed to be named by default zbackend underscore the backend technology. If you want to use username, no problem. You can extend this configuration to specify the exact name or the exact path of the library that you want to load for a volume. So here with those simple two declarations, Zeno will look in some known paths for libraries for those libraries and will load them at startup. Then we have the storages section. So that's where you declare all the storages that you want. So you will declare, for instance, here for each storage, the mandatory part is the key expression for subscription and queryable, as I showed previously. There is an optional configuration, which is strip prefix. So what the strip prefix is for, it's actually because you may have, for instance, the declaration of a key expression with a same prefix, which is, for instance, demo / my company / my region, whatever. And you may not want to have all this prefix to be stored for all keys in your storage. That's just maybe sometimes useless, and it just wastes some space in your database, right? So because it's always the same prefix, no need to store it for each key. So you can have an option in storage configuration to strip this prefix before to store it in the database. Still, when you have a query that is getting the Zeno data according to the original key of publication, the storage will do the translation, automatically retrieving the correct key expression in the storage, and will re-add the prefix. So when your querier will have the full path, the full key expression of publication back in its reply. Then you have a volume section here for each storage, where you have some specific configuration of the volume for this specific storage. So for instance, here in InfluxDB, we specify that we use a InfluxDB volume, so the one which is declared here, and we specify that we want a temp underscore DB database to be used. And here we specify that if this database doesn't exist, the storage will be allowed to create the database in InfluxDB. And you may have very other specific configuration depending on the backend technology. For instance, for InfluxDB, you may add here some extra credential, which might be different from the one for connection, which are admin credential. And here for storage, you may want to use user credential rather than administration credential. So each storage has its own set of configurations that is described in the README file for each repository implementing the backend, so in GitHub. So now let's go with a few examples, few demonstrations. And the first set of examples is about geo-distributed storages. The first one for this demonstration, what we did is that we have 4 VM virtual hosts deployed in a cloud. So we are using Linode Cloud, but you can use whatever cloud you want, Amazon, Azure, or Google. Anyway, all that you need is a VM, Linux, Windows, whatever, to deploy a Zeno router and with a public IP. So we have public IP, but we also deployed some configure some DNS for those public IPs. So they are all accessible with those host names. So us-west.zeno.io for the router on West Coast, US East for East Coast, EU for Europe here deployed in Germany, and AP for Asia Pacific deployed here in Singapore. So here in this terminal, I have one terminal in each of those virtual hosts. So one in Europe here, one in Asia Pacific, one in US West, one in US East. what I will do now is I will just at first show you actually the configuration that I'm using for those router. So let's have a look to this configuration. So here I'm in the JSON 5 for the configuration of a memory storage, for a router for a memory storage. I specify an ID, so I always know which one is each router. And I specify the connection to the other 3 other routers in the system. And then I have the plugin section. So the plugin section, I also deploy a REST, the REST API, the REST plugin that you can access on port 8000 for each router. And here I have the section for the storage manager. So in this storage manager section, I will use the memory backend. So as I mentioned, no need to declare a memory volume because it's here by default when deploying. So what I do for my storage here, I declare a storage on a key expression. So it will be demo/uu/star. And I will specify this storage to use the memory volume. So you see, it will be the same for all router in the system. Each one will have its own storage using its name as a key within the key expression. So I already have 4 distinct key space to store data, each using a geographical suffix in the key expression. So now let's start all of this router. The one here, so with name storage, I will copy paste command line. Okay. At first, let's see what we can get from the admin space. So if you remember previous session, in Zeno we have an admin space which is accessible by any Zeno API, so including the REST API. And for here, for instance, on the admin space, I'm querying all the routers and within each router, all the storages. So I get information about all the storages that are deployed in my system. And I can see here that my memory storages are all correctly deployed. So I will just copy paste this in this URL in the chat, so you can have a direct look and you can see also this, and you can, if you want, you can also experiment with the admin space to see the other information available in the admin space. Okay, now let's have a look and see what we can do with the storages. So I will use in here, I'm on my local host, and I will use this local host to perform some publication operation using the REST API. So for this, for instance, I'm using the curl command to send a put HTTP operation to the REST API of Zeno on the Zeno router running on Europe. So here I'm publishing the data test-EU on EU REST API, and this will be a publication on this key expression demo/EU/test. And now from here, for instance, if I do a query on demo/star, so I will here again copy paste this URL so you can have a look and see all the publications that are done. So here, my query here from the browser is going to the REST API deployed in Europe and is querying Zeno, all the Zeno storages deployed in the system to get all publication in matching this key expression. And now I can also play with this and perform some other publications. So for instance here, I will also perform this publication, but now I will publish this in demo/ap/test. So it means this publication is going here in Asia Pacific. Still connecting just to Europe, I get both data which are stored in Asia Pacific and in Europe. And I can also publish actually to US West, but not via Europe, but via Asia Pacific. And still, I get all the data that I want. So you can play with this if you want. You can have made some publication here. I just copy paste, for instance, this command here in the chat, and if you want, you can copy and edit and publish what you want in the storages. So on the query side, I can also get everything from different points, right? I can query also Asia Pacific, and still I get all the information from anywhere. I can query only the Asia Pacific storage, and I get only the response from Asia Pacific. I can query only the European storage. I get only this one. So you can see here we already have a complete distributed, geographically distributed storages with geographical key space deployed anywhere around the world. And still I can access the data from anywhere, not knowing the exact location. I don't need to know the exact location of the storage. All what I need is an entry point in the Zeno system, one of those routers or any other routers that I can deploy around the world that will be interconnected to those routers. So now let's have another example. So what we will see now is a distributed website. So what I did for this demo is that I generated the Zeno.io website in a static way. So all the HTML files, the JPEG files, the images, the styles, the CSS, JavaScript have been generated. And I split all this website on various file systems in my 4 VMware. So I have all the HTML and only the HTML in Europe. All the images are stored in US East Coast. All the styles and JavaScript are stored on US West. And on Asia Pacific, I only have the index.html pages. All of these are deployed on disk. And what I did is that I configured, I will show you the configuration to deploy a file system storage in read-only mode. So you cannot write in this file system. It's readable only from Zeno. And I also deploy the web service plugin from Zeno, which is a little bit different of the REST plugin. The REST plugin replies with JSON structured information, because it might get back several replies, right? When you do a query on demo/star, you get several replies. So what you get really is a JSON file, a JSON structure. But the web service here doesn't wrap the reply in a JSON structure. It just get back the payload. So it can be used really to browse a website, for instance. So let's have a look. I just stopping for now the routers, and let's have a look to this configuration. So it will be the configuration website. So increase here this so we can have a deeper look. So similar configuration, still the same for the ID of the router and the endpoints. I just added the web server plugin here as another plugin, and within the storage manager I added a file system volume with default no configuration, so it will go to the default directory. I still have the memory storage that are deployed, so you will be able to still use those. And I added another one, which is website, using a key prefix www/star. I strip this prefix to not be bothered by this in my file system. And for the storage, I use the file system storage in a subdirectory named website, and it's configured to be only readable, so read only true. So now if I have a look into Zeno, so this directory, so this is the default directory used by the file system backend. And under this, I created the website directory in which I set all the HTML information. So here in Europe, we have HTML file. In Asia Pacific, there is only the index HTML. In US West, there is all the JavaScript, CSS, and configuration of the site. And here in US West, we have all the images only. So now let's start all the routers with this configuration. Here in Asia Pacific, West Coast, East Coast, and Europe here. So I'm checking now the storages. Okay, my storages are all there. We can see here in website where they are using the file systems they are using. And now what I can do is go, for instance, on the website here using the port number of the plugin file system, which is 8080, which is different from the REST API, and the suffix, the prefix www. And by default, this gets the index.html page from Asia Pacific, and all the other information are get back from the various storages depending where they are. But the browser actually doesn't need to know where those data are deployed, right? It just gets this from Zeno, and there is no issue with this. You can see the full website is can be browsed. You have access to everything. We have access to the images and so on. But now, what if I'm stopping, for instance, the router in East Coast, which is hosting the images? Well, of course, I lose all the images. Starting it, reloading the page, and it's back. Same for the style, for instance, stopping the host hosting the style, and here I'm losing all the style, all the CSS, and so on. Getting back, and I get everything. So you can have a quick look also. I will copy paste here in the chat the URL, and you can browse the file. And of course, you can also change it. For instance, if you browse from Asia Pacific, they also deploy the web server plugin here. You have access to the exact same website content. Same from US West Coast, for instance. You can already see here that you can have load balancing on a website. You can connect from various endpoints in the world. Still, all the data you get will be fetched from various storages that can be deployed anywhere around the world, and that can be load balanced in this way. So, what else can we do with storages in them? So the next example will be time series. So time series storages, for instance, we have InfluxDB storage. So InfluxDB is a time series database. So we can map all the publications that are made into a InfluxDB storage, and InfluxDB will store all the history of publication made via Zeno or via any other middleware that are bridged via Zeno, by the way. For instance, you may have all the in a ROS system, in a robotic, you may have InfluxDB database that is storing all the publication made on the twist topic. So twist is to drive the robot, to send some messages to make the robot to move. So we can have a storage in Zeno that will store all the twist messages in InfluxDB. And later on, you can imagine, for instance, to have an application that will get the information back from InfluxDB in Zeno and will replay those information in Zeno, and then those information will be bridged to DDS. So if you're interested in this demo, I made this demonstration at ROSCON in Kyoto this year, and you can find the presentation online on YouTube, for instance. So let's see how we can configure the InfluxDB storage. In the plugin section, you declare a volume on InfluxDB, so using the InfluxDB backend, and you need to specify the URL of the InfluxDB server to connect to. So here we'll connect to a local host InfluxDB server that I will deploy, and it will be connected via HTTP because that's the only way to interact with an InfluxDB server. Even if you look at the InfluxDB API, they're all using HTTP. So has storage, an influx storage, and we'll use the key expression demo/influx/**. I'm configuring also to strip this demo/influx. So for InfluxDB, I will get only the real key stored inside because I don't need to have each key storing demo/influx. That's a prefix which is irrelevant for what I want to store. So I configure the volume to use volume InfluxDB. I create a database named demo, and it will be created by default if not existing. So we have, I will use here the zpub example. That's an example we provide with all the Zeno API in Rust, in Python, in C, even with Zeno Pico. And I will connect this zpub to eu.zeno.io and will instruct it to do publication on demo/influx/test. So all the publication will go to the router, which will forward to the storage, which will be in InfluxDB. And later on, we can get back the data using curl, for instance, and we can see how we can leverage some extension, some queries specific in the key expression for Zeno with the help of a time range. So that I will explain during the demonstration. So let's see this. So here, for instance, I will start with deploying Docker. So here I'm running InfluxDB in a Docker container on the host. It's connected. I will stop this the router in Europe. I will just show you quickly the configuration file I'm using. So here, it starts again from the same files than previously, still the same IDs, the same connections to the three other routers, and still the REST plugin, the web server plugin. I kept also the storages for memory, for website, and in the volume, I just added an InfluxDB volume here with the URL specified to localhost, so the local InfluxDB database. And here is the declaration of the influx storage using key expression demo/influx/**, stripping the prefix, using InfluxDB volume, and creating a demo database for the storage. So now let's start this configuration. Okay, and we can see here already, here in Docker, we can see the effect of this storage. The Zeno storage queried the InfluxDB server to show all the database, looking if there is a demo database. There is not, so it performs a creation of the database demo. So now I will here start the Zeno pub example. So I'm using Python here. I'm running example /zpub.py -e connected to the Zeno router in Europe, and using the key expression demo/influx/test. So here, the publication start, and we can see here in the logs all the publication coming into InfluxDB. So let's have a look here to our expression here. So if I change this to be demo/influx, I made a typo. Here I get always the latest publication. So that's the default behavior of Zeno, even with the InfluxDB storage. By default, when you do a query on InfluxDB storage without specifying a time range, you get always the latest value. So for instance, I can show you here the exact data that we get in JSON. So for instance, here I'm querying from Asia Pacific, db/**. I just get the latest one, and you can see the JSON here. We have the key influx demo influx test. We have the value, which is this sentence. The encoding is text plain, and I have here the Zeno timestamp, which is the exact Zeno time plus the source ID. So here it will be the identifier of the first router, which is actually the European router for which this publication is connected to. But now let's have a little play with time ranges. So time ranges in Zeno is specified with in the query part of the selector, so after a question mark, and we use the property _time, which is reserved for Zeno. And what we do, so I will just change my curl command here to use the -g option for curl to not interpret the brackets. Otherwise, by default, curl will try to interpret the brackets, and this will cause troubles. What is a time range? It's an expression in which you specify a start time and a stop time. So here you have the first bracket for on here you're supposed to have the first time. So let's put, for instance, now -10 seconds. So this syntax is quite similar to the one used by InfluxDB. InfluxDB use some little bit different. It's no parenthesis, open parenthesis, closed, -10s. Here we specify this way. But you can also use here real time in the format of timestamp. So using this specific format for a time, for instance, this complete time zone format. So now -10 seconds until now. So what I get here is 10 seconds of publication. So here from 175 until 183. So we may miss someone, but that's because of the latency that we may have with Asia Pacific. So let's, for instance, see what we get from Europe. Here we are 202 until 211. And I can also, for instance, if I want 30 seconds of publication, which are 50 seconds ago, I can do this -50 seconds until -20 seconds. I get the history of publication. So here I will just show where we are in the publication. We are at 240 something. If I do this again, I get the past publication 20 seconds ago. I can also get everything. So everything, I just remove the start time and the end time. So it's only bracket dot bracket. By default, the start time will be Unix epoch, so long time ago, and the stop time will be now. And here I get everything from the beginning. So I won't browse everything, but yeah, I get the full history of publication. So I will just copy paste now, for instance, this expression in the browser and in the chat. And you may have a test if you want, or you can even browse here, because the same expression is available here in the browser. We can do, for instance, now minus 20 seconds. And now minus 10 seconds. Oh yeah, no, in the browser it won't work because actually, yes, the browser, no, it should work. Let me, yeah, I forgot equal here. Here we are. We have the list of publication here. So I'm copying this link into the chat here. Okay. Now, a last example. So actually, when you have several storages which are serving the same key expression, you might want them to be replicated, right? It makes sense for fault tolerance purpose to have all your data stored in various places around the world in case of fault tolerance, in case of fault of one of your cloud or one of your routers. So with Zeno, you can specify some replication, and we developed recently an alignment protocol, which is actually named anti-entropy protocol. My colleague Srija Nair performed a very interesting blog on the algorithms used for this anti-entropy protocol that is implemented for the Zeno storage. To demonstrate this, I will use 4 memory storages, all deployed using the same key expression, demo/ft for fault tolerance /*. And I will configure those replica here. So it's again a storage named demo replica on key expression demo/ft/*. I strip the prefix. So here it's showing file system. Actually, I will use memory for this demonstration. And the replica configuration is here configured with a publication interval, a propagation delay, and a delta. So I will let you have a look to Srija's blog to know all the detail about those configurations. They are really related to the dynamic of your system, depending mainly on the latency you may have between all your hosts. So here, for instance, a propagation delay of 200 milliseconds is because, well, the average, the biggest average latency we have is about 20 milliseconds between all the hosts, for instance, between Asia Pacific and US East Coast, or between Europe and Asia Pacific. So I will just stop again the router and show you quickly the JSON file. So it's /replicas. So it's still cumulative, so it's still the same as the previous example with InfluxDB, but this time I added this InfluxDB, this demo replica storage on demo/ft using file system. Yeah, it's using file system. And yes, it's declared as read-only, and there is a replication configuration which is here. So let's deploy this one. So here, let's have a look to what we have in the file system for this demo. So there is nothing yet in the backend. So just to stop the log, I will stop here the publication so I can show here what we have. I can't suspend it, so I need to stop it down. I will just restart it in background in case you want still to experiment with InfluxDB. It's running in background. And here, Okay, all the fault-tolerant storages are empty on file system. So now I can perform some puts here on this file system. So for instance, I will do a put here on demo/ft/a. So if I do ls again, so hold on, not this one, this command. Here you can see in each storages the A file have been created and with the content which is A. So I can now I will stop, for instance, the one in Asia Pacific. So I'm stopping storage router and storage in Asia Pacific, and I'm publishing now demo/ft/b. If I do ls, okay, it has gone to Europe, it has gone to US West, it has gone to US East, but of course not to Asia Pacific because this one is down. I'm stopping here US East Coast, and I'm doing again a put on /demo/ft/c. It has gone to Europe, it has gone to US West, it has not gone to Asia Pacific, and not gone to East Coast. So you can see the status. So here we have a divergence. We have a conflict between the databases. One gets some information, and the other ones didn't get those publications. But now, if I'm restarting, for instance, the router in Asia Pacific, it will perform the alignment. And now, if I do ls again, what we can see is that the B and C publication have been copied back into Asia Pacific. So the replication occurred between this router that I just started again and the other routers, and all the latest publications that have been stored by online routers are now been copied to this storage here. So on US East Coast, still nothing. So now I'm deploying starting the router. The alignment protocol is occurring, and if I do ls here, the alignment eventually occurs here. You see there is a little latency, which is tied to the propagation delay that is configured here, but also to the delta. It's a delta check, so we check only if there is a mismatch between storages each 1 second. So you have this delay plus the delay of propagation. So it might, with this configuration, it takes just few seconds to have the complete alignment. Okay, so I can let you play with this if you want to go on and continue to do some publication or some retrieval from Zeno. You can still perform some curl operation or directly browse with the browser. And we are at the end of this webinar. So thank you for your attendance. And yes, don't forget to visit our website, to visit, of course, our GitHub repository where all the backend implementations are developed. So you can see in Eclipse Zeno, all the backend are prefixed with Zeno-backends. And you will get all the details of implementation code. Also in the README are all the detail of configurations, the configuration properties that are available for each backend. Join us on Discord if you have questions, and of course, if you have questions now, just shout.
Hi, Julian. Thank you for this webinar. You've actually been live for over 15 minutes now.
Thank you, Daniela.
We actually have a few questions, like 4 or 5 questions. Our team answered some of them, but I'm hoping you can give us more in-depth answers and maybe some examples where you can. The first question is, Can DBMS be integrated with Zeno?
So DBMS, yes, actually, we made in the past in implementation in the previous version of Zeno, which was developed in OCaml a few years ago. We made a backend for SQL, so it was leveraging a library which was able to drive different SQL databases, MariaDB, Postgres, and another one. And yes, we have the plan to reintroduce also to redevelop in Rust this backend for DBMS, so for SQL-based databases. That will come probably this year. Yeah.
Okay, thank you. The next question is, how do I control replication in Zeno? And maybe you can give us a concrete example as well.
So, I gave already the example in the demonstration. So the replication is configured when you declared the replica section in the configuration of your storage. So all the replicas using the same key expression will be considered as replicas with each other. So you really need to have the exact same key expression used in all your replicas, the same configuration of replication. They will discover each other via Zeno anyway, and they will be able to exchange and to align with the help of the anti-entropy algorithm. Everything is automatic as soon as you declare your storages to be replicated with the same configuration.
That makes sense.
And just
we have a question
last point,
from class.
it's not dependent on the backend technology, right? The replication algorithm is independent of the backend technology. So you might, for instance, imagine to have a storage on /demo/ft/star on file system, the same key expression on memory, the same key expression on RocksDB. So heterogeneous technologies using replication. And you will have a replication of your data between a storage on file system and a storage on RocksDB and a storage on memory. The mix of technologies is supported in Zeno.
Okay, thank you for that. Another question from class. Is there also a way to set the history date in samples or time, or is it only visible in the DB and not in Zeno?
It's available in Zeno actually. When you do the get, when you see here, for instance, the get which is performed on the REST API, it's really a reply from Zeno. So if you do the get with the Rust API or Python API or any API, what you get is really the samples that have been stored in Zeno with its original encoding information and its original timestamp. And for InfluxDB, actually, when the publication come with a Zeno timestamp, in InfluxDB, we reuse the timestamp from Zeno as an entry in InfluxDB. So even if you go through the InfluxDB API and you get the information, it will be stored with the Zeno publication time, so the Zeno timestamp inside InfluxDB. And on our driver, Zeno get back this timestamp from InfluxDB actually.
Okay, thank you. Can I use different backend in the same Zeno application? Is this transparent?
Absolutely, it's transparent. So as you can see here, I still have everything which is running. So for instance, if I do a query on demo/star, what do I get? I get the one from FT, for instance, only, yes, because we didn't do any put. So that's the one on file system. But if I do a get, for instance, on, let's say, I will do again, start again the one on InfluxDB, which should work. So now I do the query again. No, it seems to be not running. I see. It seems I have a. Yeah, it's because the Influx was not running in this one. So I'm starting here again with Influx. Here we are. It's available here. So if I do ** now, you see I get a mix of reply, some replies from the file system storages, which I use for replication, and one reply for InfluxDB, for instance. And if I do again put on /demo/u/test, so that goes to memory, and here I go also the one from memory. So you see here, there is already a mix of technologies, one from memory, few from file system, one from InfluxDB. So everything is mixed together, and you can access everything from Zeno from anywhere.
Okay. We just hit an hour of this webinar, so we have time for one more question. The last question is, can I query Zeno storages from Zeno Pico?
Absolutely, yeah. Zeno Pico, in the same way than all the other APIs, support query operations, so the GET operation. And as soon as your Zeno Pico peer client is connected to one of the router anywhere in the system, it can do a GET operation, and the GET will be routed by the Zeno router up to the storage. The storage will reply, and the router will route back the information up to your Zeno Pico client. That works with Zeno Pico also.
Okay, well, this is everything we have time for today for this session. Thank you everybody for joining us live. If you have a colleague or a friend interested in Zeno and Zeno Pico, please tell them that we'll have another session of this webinar at 6 p.m. Central European time, and they are more than welcome to join. Anything you'd like to add, Julian?
Thank you for your attention, and yes, Merry Christmas and Happy New Year for the coming weeks.